Hi and welcome to this, our little lesson on piecewise hybrid functions. Now what do you mean by piecewise and hybrid functions? Whoa! Well, if you've got a hybrid car, that means your car operates on a bit of electricity and a bit of petrol, gas, fuel, whatever you're saying. So hybrid has something to do with mixing stuff together. For those of you who are unfortunate enough to be taught by me, you will find the work you need to do just here. Thank you so much. But as is normal, bit of a recap. Now, obviously, you guys have been away on holidays for a bit, and so we've already talked extensively about functions. We've covered what a function is. Now, remember, there is a difference between a relation and a function. And I think sometimes we as maths teachers make mistakes by using the word function all the time, when in fact a function is a specific thing. So to go back, if you remember, a function has to pass the vertical line test. And by that it means if you can draw a vertical line through your graph and it only crosses that graph once, then it is a function. Now, everything I think other than that is a relation. So y equals mx plus c, y equals x squared, all relations, even x squared plus y squared equals 4 is a relation. But in this situation here, that would not be a function. Why? Well, basically, that is a circle with radius 2. And if we draw a vertical line through that, what do we find? Well, it goes through twice. So it wouldn't be a function, but it's certainly a relation. We've talked about function notation. So that's where you've got f with a colon, and then you've got your domain of, say, which is mapped onto real, of some function equals x squared. So again, knowing what each of these sections means is critically important. This here is your domain. This is your codomain. This is your actual function, and please make sure that that f and that f match. So you know your domain and range. And funnily enough, we talk about domains and ranges. Domains are all possible x values. Ranges are all possible y values for a particular function. Let's scroll across. So if we look at y equals x squared, for example, what is our domain? Now, I'm going to draw a quick sketch of y equals x squared. And what I'm saying is, bearing in mind this axis goes all the way to infinity and negative infinity, I want to ask you the question, are there any numbers between minus infinity and infinity which we can't square? Right, so think of the number, I don't know, minus 6 or 7 or 1,346,902 or 920. Are any of those numbers not possible to be squared? Well, actually, there is no number between minus infinity and infinity that can't be squared. No reason in this world why it can't be squared. And so, in this situation, we would be saying our domain is equal to all real numbers. Now, I would prefer you to start using methods notation, and domain is given by x in this situation, is a set of, or is contained within a set of, and this situation we would do real. Or we could say x is a set of numbers from, oh no, not square brackets, chillax, minus infinity to infinity. And remember, it has to be curved brackets for infinity because infinity isn't a number. So we've looked at the idea of domain and range. Well, range, whereas domain is the possible x values, range is our possible y values. Now again, if we use the idea of y equals x squared, what are the possible y values? Well, firstly, there's absolutely no part of my graph currently below the x-axis. So it would suggest that the lowest value of y that is achieved is at the value of 0. And it would appear that all values from then on, because my graph seems to stretch on to infinity and beyond. So our range in this situation would be from 0 and including 0 to infinity. We can write that in a different way. We could write f of x is a sub, or falls within a subset of 0 to infinity. Or we could use real number notation by saying r plus or 0, right? Because we have to include the value of 0. So this here is all positive real values, but 0 is neither positive or negative, so we have to say or 0. This is all work we've done previously. We've looked at real numbers and integers, we know that. We've looked at the vertical line test to test for one-to-one functions, right? To test for a function. And we've looked at why and how we restrict a function. And again, to talk about why we would restrict a function, if we have this function here, again, let's make it nice and easy, y equals x squared. Well, it might well be that we don't always want all of that function. So we might say, for example, well, I want to ignore everything on the left-hand side of my turning point. Well, the way we do that mathematically is we say that we limit the domain. Right? So we limit the domain. This is just another way of saying, well, we're going to ignore half my graph. So in that situation, bearing in mind the domain is normally all real numbers, well, I only want now from 0 through to infinity. So what I would say is I'm going to limit my domain to now make my domain equal to 0 to infinity. That's one way. Or again, real plus or 0. So there's a number of ways of doing this. And why do we need to limit the domain? We'll come back to later. But ultimately, you can write, if I wanted to write this in function notation, I would say f colon 0 to infinity is mapped onto real function of x equals x squared. And anyone who reads this function will now know that I'm only interested in the section between 0 and infinity. All right, we're now going to look at hybrid functions, also known as piecewise functions, and there's no reason in earth why anybody should really be taking taxis, but that's a whole new discussion, right? Uber, don't even go there. For those of you who know it, whether you get in a taxi and then get out without having moved, you would be liable to be paying the flat full fee. That's that fee that, you know, when you get in and the taxi pulls away and then you suddenly starts hitting buttons and before you know it, you're $4.50 and you haven't even moved anywhere. That's a flat fee. So automatically, before you've moved and for a certain distance, that flat fee kicks in. That's what you're going to pay to use the cab, and that distance is very, very short. Then what you'll notice is after a certain distance, the cost of the taxi starts to go up. That little counter thing that says money starts to whir ridiculously quickly and ridiculously high. And then after a certain distance, even more so, it'll get faster and faster and faster. Now, most cabs will have some sort of information on the door that will tell you the cost per kilometre at certain times, right? So, as I say here, it would be great if everything in life could be described by a parabola. And here is my favourite parabola, y equals x squared. But it isn't. And the cab is a brilliant example. So, as I say, when you take a taxi, before you even leave, all right, or just as you leave, you get what's called a flat fall. This is a fixed cost for using a taxi. Then, for a certain distance, that price will be set at one value per kilometre. And after a certain distance, it will be changed. Now, we don't want to draw three different graphs because there are now three conditions, condition 1, condition 2 and condition 3. We don't want to draw three separate graphs to explain those when we can actually put them all on the same graph. And that's exactly what I've done here. Right? So if we notice along this bit here is my distance, right? My distance traveled, and up here is actually my cost. So this point here says that in 3 kilometers, I will be charged $2.50. So actually, looking at the graph here, this is my flat fall. This is that first fee they charge you. Now, I actually say, you know, I've got here that it actually goes to 3 kilometers. You'd be very lucky if you find a cab who'll take you 3 kilometers on that flat fall. You know, I think it's pretty much like 4 paces and then it starts to rocket up. But anyway, whole new discussion. Then you'll notice that you have a straight line. All right, you have a straight line section. So there's a definite, and I call this section here a kink. Right, that's not like the pop group. It's a kink, it's a bend, it's a definite change in direction. Whereas if we go back to the x squared curve, you'll notice every single point is smooth as it leads into the next one. This has a very definite change in direction. So this might be, as I say, this now happens up to 15 kilometers. So what this section of the graph is saying that between 3 and 15 kilometers, there's now a different cost to use my cab. And once again, there is a third section here that says, well, over 15 kilometers, so between 15 and in this situation, 20 kilometers, there is another cost per kilometer that changes. All right. Now, again, this is a oversimplification or maybe making it more hard, more difficult. But the point of it is there are 3 sections to my graph. So Flat fall of 250 for the first 3 kilometers. Then it has a rate growing depending on where you are between 3 kilometers and 15, and then between 15 and 20. So, right? So the above graph, when you have one graph showing a number of different sections, or there are kinks in them, or it seems to be different graphs joined together, they're called hybrid functions. And because the questions in the textbook also use the word piecewise or piecewise defined, just remember that mathematics can interchange that language. So, knowing that it's interchanged, piecewise, hybrid, same thing, we want to find a mathematical way of describing it, and this is how we do it. So, first things first, we use these curly brackets. And you must get used to drawing curly brackets. Drawing these type of brackets really doesn't cut mustard with VCE or with examiners. And we now know, as I've said here, that this f of x is just another way of saying y equals. So we are using these curly brackets to write 3 equations. This one here is the same as writing y is equal to 2.5, which is that horizontal line section, right? So whenever you have a y equals 2.5, it's horizontal. Here, this is the same as saying y equals 1/8 x plus 17 on 8, horrible numbers. And this line is saying, well, the third section can be described by 2/5 x minus 2. So again, let's go back. This section here is 2/5 x plus 2. That's the equation of that section of the line between 15 and 20. What did I say this next one? This section here is 1/8 x plus 17 on 8. And that's only valid between 3 and 15 kilometers. So how do we show that? Well, again, we use an idea of domains. And so that's what this section here is. 2.5 is only valid for distances between 0 and 3. Now, what do you notice? I've got less than, d, and less than or equal to 3. I'm not going to include 0 because that explains the situation that when I can get in the car and get straight back out again, they're going to charge me, right? So for any distance between 0 or slightly bigger than 0 and 3 kilometers, that's the charge I'm going to get, $2.50. This section here says that the equation y equals 1/8 x plus 17 on 8 is only valid between 3 and 15. Now, what do you notice? That has 3 in it, and that has 3 in it. But the equal sign only belongs to one of the 3. I can't put an equal sign here. The reason being is the number 3 can only belong in one of the lines of the hybrid function. By putting an equal sign on both of these, it means it belongs to both. So we, generally speaking, only put an equal sign on one of them. So I'm going to say that up to and including 3 kilometers, I'd be paying $2.50. Over 3 kilometers, which is what that means, and less than or equal to 15 kilometers. And finally, there we go. The last section was described by that equation and is only true between 15 and 20. So will you end up having to do all of this in an exam? Will you be, finding equations of hybrid functions? Highly unlikely. Although you will be expected to draw hybrid functions. Now, one of the easiest ones that we can tend to draw, but highlight stuff, is this one here. So here we go. Here is a hybrid function, and you probably noticed that minus sign switch. Yup. Right, it went from the bottom line to the top line because otherwise it made absolutely no sense. So in this section, we now know that we only have 2 sections of my graph because we only got 2 lines. We need to decode what it says. Function of x is just saying y equals. So for values of x less than or equal to 0, so values of x that are less than or equal to 0 are that way, I want to draw the line of y equals minus x. And for values where x is greater than 0, again, it can't be that 0 is included in both of those. Where x is greater than 0, this way I want to draw the graph y equals x. Now, if you don't know what these graphs look like, the best thing to do is actually just plot them. Plot the first 3 or 4 points and you can guess from there on. So there is 0. I'm going to put x is 1, 2, 3, 4, and 5. And then we'll have minus 1, minus 2, minus 3, and minus 4. So here we're drawing the line y equals x. So when y equals 0, x equals 0. When y equals 1, x equals 1. When y equals 2, x equals 2. When y equals 3, x equals 3. So nicely, what do I have? And this is going to look ropey because I can't draw things accurately on here at this moment in time. I get that my line. So there is my line, y equals x. I now need to draw y equals minus x. Well, where y equals minus 1, sorry, when x equals minus 1, y would become 1. There we go. When x equals minus 2, y would become 2. When x equals minus 3, y would become 3. And I don't think it takes any major genius to realize that there is my hybrid function. I'm going to label this y equals minus x. And actually, I should get all of the marks for my exam. I mean, obviously not that wobbly line. I'd reuse a ruler or something along those lines. But important points is label the axes. Right, so my f of x and my x label, and always label the graphs with the equations, right? So label the graphs, hence writing this y equals x and y equals minus x, right? So that's one example. Let's make it more complicated. In this situation, once again, I say I'm making it more complicated. I've got two functions. I've got two parts of my hybrid function. The first one is y equals x. The second one is y equals 2 minus x. Now in this situation, the first one is for the values of x is greater than or equal to 1, and the second one, x is less than or equal to 1. So looking at this, I now can say that we're hoping there's going to be a join where x equals 1. So here's my value of x equals 1. I'm now going to look at one set of my hybrid function going that way, and one set of my hybrid function going that way. So this way is y equals x. Right, so starting when x equals 1, y would equal 1. So that's actually my start point. When x equals 2, y equals 2. When x equals 3, y equals 3. When x equals 4, y equals 4. And again, I can now draw my straight line. Now please, don't continue the straight line to 0. Don't draw this section of the line here, because that's not where my graph kinks. My graph kinks where the two values suggest. So when x is less, so when it says basically there's a join when x is 1. So undoing that part of my line, I now go back to the second part of my graph, right? So the second part of the hybrid function says I need to do 2 minus x for all values to the left of 1. Right, so when x equals 0, that would give me y equals 2. And all I'm doing is substituting values in. When x equals negative 1, y would be equal to 3. When x equals negative 2, y would be equal to 4, and then 5. And once again, I have the opportunity to draw a beautiful straight line there. Label them, y equals x. Label, y is equal to 2 minus x. And I'm pretty happy that I have my hybrid functions. Now, that, ladies and gentlemen, is the end of the discussion of hybrid functions. Let's just recap very quickly. It is really important when you have a hybrid function that you realize that the curly brackets describe a hybrid or a piecewise. These things here are the equations of the lines. They can be curves. There may be quadratics. And these things here are the domains for which they are to be drawn, or those particular graphs to be drawn. So as I say, for this one here, when x is less than or equal to 0, we're going to draw minus x. And for this one here, when x is greater than 0, we're going to draw x. Nothing more to it, really. So, thanks very much for watching. I look forward to seeing you next time. It's been so great having you watch this video that I'd like to see you again and again and again. Wow, we could make some amazing maths together. So, if you'd like to, and you'd like to be updated as to when I upload new videos, why not subscribe by clicking the button on the right? Otherwise, if you want to click and see another video created for this type of series, then click the video on the left. All right, well, you have an awesome day, and I look forward to seeing you again.